All right, gang. Can I have your attention, please? This is one of these where this reactant A isn't held constant for any of the trials. B winds up being held constant for 3 of them. Now, why would somebody do their experiment this way? If you know you're trying to find a rate law, why wouldn't you just hold that constant for 2 trials and hold that constant for 2 trials and vary the other? I don't know why they do that. But a lot of the problems that involve these kinds of analyses, they do this to you. I don't know. Right. I know.
Sean was shaving me today.
Yes?
So I was thinking because my grades are going up. Your grades are going down. I just start laughing.
You really can't go down from the roof. You're going to take this, you might need it.
We should box someday.
You say I get 6.
Just based on my experience myself. No, not with you. All right. So I would say for this one, probably easiest to use trials 1 and 3 to find the order of A. Because B is held constant. So we're going to find A. When A doubles, and that's the only thing that's going to affect the rate would double as well. So that means A is first order. I really hope by now that's an easy thing for you to do and see. Now, the B is not so easy. It doesn't matter which 2 you choose to find B. You can't use 1, 2, and 3, though, because they're all the same for B. So anything with 4 would work. I would say let's just use 3 and 4 for finding B. Now, we know that A is first order, so that when the concentration of A doubles, the rate would double as well. So it was 3.2, that becomes a 6.4. That correction is because of what happened with A. A is first order, and it doubled, so that doubles the rate. Now, B is going to get cut in half from 0.8 to 0.4. So from that quantity to that quantity, how's the rate changing? It's getting cut in half. It doesn't matter. Go ahead. What is the order of B? We cut the concentration of B in half, and that caused the rate to get cut in half. So that means B is first order as well. The same change that happened to the concentration happened to the rate. That means first order. I told you at the beginning of this chapter that first order is definitely the most common. You're probably seeing that now. There's a lot of first order things.
Man, I don't even remember the first one.
Okay. Now what I'm going to do for a big part of this class, is talk about mechanism, even though we just had a reading assignment about it and you did the reading quiz. This is going to, by a big stretch, repeat what you read about in the book. I think it's important enough, though. You know how a couple days ago, or yesterday, I was talking about how we're going to be spending all this effort to find the order of the reactants, but what does order really mean? Well, if you understand the mechanism, that will help us to understand what order really is. So the mechanism of reaction involves what steps are involved with the reaction. Some reactions have a very clear, well-defined mechanism. Others don't. One mechanism I can think that's very popular and common is the Krebs cycle in biology. You ever learn about the Krebs cycle? Some people have said that in 9th grade bio they had to learn about the Krebs cycle. Also known as the citric acid cycle. I don't know if you've ever called that. I had biochemistry as part of my degree, and I will tell you that biochemistry was my least favorite of all. Not because there's anything wrong with it, it's just that my brain didn't do well with it. And I didn't enjoy it. I didn't like learning about it. I knew I wasn't going to go into the medical field, so I was like, well, okay, I'll take it because it's part of my program, but I didn't like it. Dr. Moore was my teacher, same name as me. It was just a drag. We had to learn every step of the 26 steps of the Krebs cycle. That is a big mechanism. And man, I still remember, no, I don't remember what it is. I remember there were 26 steps, and I didn't enjoy that at all. And then I had some students that were in AP Bio. I think they had it last year. They're seniors this year. They said, yeah, they had to learn it for AP Bio. Anybody in that class this year? AP Bio? I don't know, but they're both seniors, and yeah.
Josh is taking AP Bio and Physics C.
Yeah, yeah.
Except that they read it, but
All right. So anyway, I was saying the whole reason I even brought that up was because some mechanisms of reactions are well documented. We know exactly how they work. And then others, we don't know what they are. So we propose a mechanism. And as you read about, there's two criteria that tell us whether a proposed mechanism is valid. That doesn't necessarily mean that's how the reaction works, but it's a good guess. And those two criteria are if the rate law of the mechanism is the same as the rate law that was experimentally determined, that's got to be true. Also, the two steps, or the whatever number of steps, have to add up to the overall equation. You remember reading about that?
Yes.
What makes the mechanism valid?
Yes.
Did you say yes just so I'd be happy, or you remember?
I remember.
Good.
It was a box.
It was a box.
It wasn't. Yeah, I promise.
Okay. All right. Good. I'm glad. We're going to focus on this reaction for a little bit of time. This reaction is a simple reaction. It looks like the NO2 releases one of its oxygens, and the CO takes it. That's pretty much what happens. The NO2 goes down to NO, and the CO goes up to CO2. So, and I see down and up because one loses an oxygen, one gains an oxygen. Experimentally, it is determined that this is the rate law. Now, I've talked about before.
wait, but doesn't it have to be slow?
Why is it NO2?
This is an overall reaction. It's made up of a couple of steps. There's a couple of steps that happen. So the slow step is what determines that one. Yeah. And that was my question for you is, where is the CO in the rate law? How come CO is not in there? And why does the NO have a squared after it? Isn't there only one NO? Is this thing wrong? Remember that the rate law is not a function of what the overall balanced equation is. Just because the balanced equation has ones for coefficients does not mean that's what the rate law is going to look like. We have to find the rate law by doing the experiment multiple times. So it's found that the NO2 is second order in this reaction. And CO, what would you say about the CO order? It's zero order. It's zero order. Because zero order means that the CO concentration doesn't affect the rate. And that's fine. You can have a reactant that's zero order. We've seen that already in some of our examples. One proposed mechanism would involve these two steps happening. This would, we think, be valid because they add up to the overall equation. And as long as the first step is the slow step, that would reflect what the observed rate law is.
So you would have it squared because why?
Because this is the slow step, so it would be K times NO2 times NO2, which is NO2 squared.
Wait, could you say that last one?
Yeah. I am assuming the first step is the slow step, because the rate law of the slow step would be K times NO2 times NO2, which is that. So again, I'm going to go through a lot of the things that the book said. I'm going to give you lots of terms that you already have read about. So don't feel insulted. I just want to make sure that you understand what each thing is. Now I'm going to recopy every slide that I do this with. I'm going to have this, so you don't have to write it every time I go to another slide. It's the same mechanism that we're going to be talking about. We good? Can I move on? Okay, so here's our two steps. Just some terminology. We have an intermediate present in our mechanism. The NO3 gets made in step 1 and then used up in step 2. So NO3 never shows up in the overall equation. That's what an intermediate is. I think I asked you about an intermediate on the reading quiz. Yes.
Yeah. No.
And there were two in that reaction or mechanism. Then some other things. It's important to understand what an elementary step is. A mechanism is always going to give the elementary steps. An elementary step just means that that step of the reaction is not made up of simpler steps. That's it. So this reaction occurs in two elementary steps. The two NOs react, and then the NO3 and the CO react. And that's it. There's nothing else that's happening in the reaction. Mr. Hevel is next door.
What would the final reaction be? I mean, like, what would it be called if that's called those? If those are called elementary steps?
Then when you add them together, you get the overall reaction. Yeah. So that overall reaction, this would not be considered an elementary reaction because it's made of two other steps, or two simpler steps. Sorry. So yeah, the book introduced a term called molecularity. Molecularity has to do with how many particles have to collide with one another to cause each step to happen. The molecularity of both of these is 2. We would say that both these steps are bimolecular. Just how many particles have to run into each other in the reactants. Oh, yeah.
So just the number of reactants?
Yes, we're only thinking about the reactants. Yep. Everybody good with this slide? All right, moving on. Here's our mechanism again. And now there's a couple other things about this. Because each one is an elementary step, it's not made of simpler steps, you can give the rate law for each single step of the reaction. So the rate law of the first step would be K times some constant times NO2 squared. And then the rate of the second step would be some constant times NO3 times CO. Those constants, by the way, are not the same. Because one of these is a slow step and one's a fast step. So the faster step is going to have the higher K value.
Do you want to achieve a smaller K value? Or is it...
Well, no. I mean, normally we would analyze a reaction. Some reactions we want to go fast, and some reactions we want to go slow. If we were trying in the business of like trying to produce pharmaceuticals or chemicals or whatever, we would want our reactions to go fast because we want to produce as much as possible in a short time. What reactions would we want to go slow?
Rusting.
Yeah, things that are corrosive, right? Like rusting. We want rusting to be a slow reaction. So if we have rusting as a part of a procedure, like an automaker, rusting is bad for their industry, so they want to do everything that they can to try to slow the rusting process. So what can they do? Well, they can paint over iron is one thing. Or they can melt iron and mix it with other things that prevent it from rusting. So that would slow down the K value too. Those kinds of things, yeah. Yeah.
Wouldn't a battery also be one?
A battery, absolutely. Yeah, you want a battery to last a long time. That's a great example. Yep. Okay, now here's something that I find very interesting about this reaction. Remember what the overall reaction is this. These are the two steps, but the reaction is NO2 plus CO yields NO plus CO2. I want you to notice in the overall reaction, these are our two reactants. So physically, we have to take a container and put some NO2 into it, and then put some CO into it. But it turns out when these two are reacting, the NO2 and the CO don't ever have to interact with each other. Look at the mechanism. You have two NO2s that combine together, and they'll make an NO3, and then that NO3 reacts with the CO. So these two reactants don't necessarily have to even touch one another. It's kind of interesting how that can happen in chemistry.
So nothing will happen if you touch?
No, they probably won't react with one another. Or maybe you'll get a side product, which can happen. You get something that you don't want. the rate determining step. When we have our mechanism broke up into the two elementary steps, the one that's slower dictates how fast the whole reaction is. The one step might be really, really fast, but if your rate determining step is very slow, that means the whole reaction is going to be very slow.
So that's what you base the...
Yeah, so the rate law is based on the slow step, always. The rate determining step, an analogy of that would be like this. If I wanted to race bikes, maybe I got into a race in which I had to have a partner, and when both partners finish the race, then that's like where my team finishes. So if I'm a very slow rider and my partner is really fast, then my partner is out of luck because he's going to finish way ahead of me, and then he's going to be waiting and waiting and waiting for me to finish, and everybody else is probably going to finish before me, and so our team would be no good. Even though we have a very fast rider, my bad performance is bringing the whole team down. Right. So, note to self, don't choose me as a bike partner.
I feel like you were a triathlon guy.
Yeah.
I've never done it. I'd like to try. Yeah. I have a friend that just did his first one this year, and I thought, yeah, I think I'd like to try it.
I did a mini.
He did, let's see, I think he was a mini try as well.
I did
It was a 5K run and 1 mile swim. I think it was 1 mile swim, and what was the bike? 10?
It was like 10 miles.
Yeah,
It's
I
12.
think it's like that, yeah. All right. So, and we know these two things. In fact, I'm not even going to wait for you to write this down. Just know that the two steps have to add up to the overall reaction, and the slow step rate law has to agree with the experimentally determined rate law. Now, we're going to do a few examples. Would you take out your handout that I gave you not last week, earlier this week? The one that says kinetic practice problems. Do you still have it?
This is the only handout you've ever given me to us. You know, before I got here, I had a binder set for you.
Yeah.
And those tests that we all
Yeah, this is nice to have example problems like this when I have to
That's
rate.
for all of the super long problems.
Yeah, that's a good idea.
I don't think people heard my joke. It was actually really funny.
The fact that you have to verify that.
I'm just saying, man, that joke was funny.
What? Regan.
Will you take a look at number 3 with me?
I'm not saying
Regan, what's your number 3?
Why are you continuing?
Just keep going. Regan, I'm
I
gonna
know, like you
Number 3. The rate law for the reaction, which it gives you, that was actually the reaction that was in your reading quiz, is rate equals K times H2 to the first times NO to the second. Which of the following mechanisms can be ruled out on the basis of the observed rate expression? So there's 3 mechanisms that are given. One of them is no good. And what we want to do is compare the slow step in the mechanism to the experimentally observed rate law. What do you think of mechanism 1? You see the slow step is the first step. We have 1 H2 reacting with 1 NO. Is that a good mechanism?
No.
No, that's our problem, right? The mechanism 1 is the bad one. Because the slow step of mechanism 1 has to have a rate law that's equal to the one over on the left. It's got to be K times H2 times NO squared. And do I have that? Oh, no, that's not the one.
So what is it?
So the number 3 is no good. I'm sorry. I was looking at the number 3. Mechanism 1 in number 3 is no good. Again, because the rate law that they gave us was rate equals K times NO squared times H2.
So what's
In mechanism 1, the slow step is just rate equals K times H2 times NO. It's just what's reacting in the slow step. That's not the same as that, so that mechanism is no good.
Why is the NO squared individual?
Oh, because that was found experimentally.
Oh.
Yeah, that had to be found separately. Yep, so they're just giving us that value rather than having us find it. Now let's take a look at mechanism 2 and 3 as well. I suppose it's possible for there to be more than one mechanism that's bad. The way the question is worded, it kind of leads us to just one being bad. But let's see if the other two are okay. Mechanism 2. Take a look at the slow step in mechanism 2, and does that rate law agree with the experimental rate law? It does. It does. Because the slow step has one H2 and two NOs, and that's exactly what they have in the experimental rate law. You okay with that? Do you see what I mean by when I say experimental rate law? Over here where I'm pointing, they give it right under the chemical equation. That's the experimentally determined rate law. All right. Now let's take a look at mechanism 3. We all need to look at mechanism 3 because something funny happens there. I wrote down up here the first two steps of mechanism 3 because we need to talk about this. Yeah, got a question?
Yeah. So for the overall reaction, that's when we use the order, but then for the experiment, like for the mechanisms, that's when we use the coefficient. It's for the exponent. Sorry.
Say that one more time.
So for the overall reaction, we use the order. So if we find experimentally for the exponent.
Yes. No, you don't use the coefficients for the overall.
Yeah.
You have to use the data that's given, like we did in number 1, where you find the order of everything.
But then in the mechanisms.
In the mechanism, yeah. When you have elementary steps, you can just use what the coefficients are. Yep. Yep. Okay, everybody, stop what you're doing. Look at number 3. Mechanism number 3 in this one. I have it up here. Here's the first two steps. The first step was fast. The second step is slow. Now, if we look at the rate law for this, the slow reaction, the rate would be K times N2O2 times H2. Does this agree with the experimental rate law? No, it doesn't. The N2O2, if it were NO squared, it would, but it's certainly not NO squared, it's this. So at first it looks like, nope, it's not a good rate, not a good mechanism. However, what about N2O2? What do you see about N2O2 in the mechanism? What would you call it? Yes, it's an intermediate. We can't really, the N2O2 we didn't start with, we don't know what its concentration. So when I put the brackets around, that means the concentration of N2O2. It's an intermediate. It doesn't have a defined concentration. So that means, we're going to move that over. Hey guys, thank you. That means this. I got 2 bullet points for you that I want you to take note of. Number 1, we don't define a rate based on an intermediate. So we don't define a rate based on intermediates. Means that I'm not satisfied with the way this rate is written because it's got an intermediate in it. So what do we do with it? How is N2O2 produced? Take a look at the first step. From 2NO, but look at that arrow. In fact, it even told you when it was describing fast or slow. It didn't just say fast, it said fast equilibrium. That was a hint. This is made at equilibrium. What do you know about equilibrium reactions? They're reversible. They suck? No, that's not true. They go in both directions. They can go to the right and they can go to the left. Remember, equilibrium means the reaction, it comes to a point of comfort. It just stops. So when a reaction comes to equilibrium, there's a relationship between the concentration of the reactants and the concentration of the product. That relationship is given by the equilibrium constant K. So here's what we do. When you have an intermediate, if the intermediate in the rate law was made by an equilibrium, you'll replace it with what reactant made it. All right. Yes, as long as it was made by an equilibrium. Yep. And now I'm going to show you several examples where this is done. But write this down as a second bullet point. Replace, this is not going to hold out for me. Second bullet point. Replace intermediates with the reactants that made them. So that means the N2O2 is going to get replaced with whatever made it. And look at what that is. It would be NO squared. Because remember, we will use the coefficient only for elementary steps in the rate law. So this rate is now rate equals K times NO squared times H2. The H2 wasn't intermediate, but the N2O2 was. And so I'll replace the N2O2 with what reactant made it. Yes, Avni?
So what if it was rate for like 2 reactants?
Then you'll put both of them in.
Okay.
You'll replace that intermediate with both of the reactants concentration. Okay. And we'll see that. We're going to do that in a moment, Rush.
This is only when there's like a fast equilibrium as well.
Yes.
So
Yeah.
everyone's had that intermediates as well, but you don't.
Uh-huh.
You don't do those.
Right. Right. The other ones, the slow step didn't have an intermediate in the rate law because they were the first step. Okay. Can you guys turn that over here for me? So actually, we are pretty much done with the board until the end. Would you jump to number 5 now? Number 5, I told you we were going to do the last part after we had. Thanks very much, you guys. After we had talked about mechanism. So look at part 5D now. We did the first few parts of 5. Do you have the rate law written for number 5? Both of them are first order. ClO2 and F2 are first order. All right, so let's look at D. We did everything else except D. Which of the following mechanisms is consistent with the rate law that we found in part A? Let's do 2 first, because 2 is very obvious. Is 2 a valid mechanism? No, it's not. The slow step has just F2. It's got to have ClO2 and F2 in it. So no good. Jess, you have this handout that says kinetics practice problems?
Yeah.
You have it, okay. We're just talking about number 5.
So it's 1. Okay.
So yeah, we know it's not 2, so it's got to be 1. But why is it 1? It's 1 for the same reason as what we wrote down over there. You can see that the first step is a fast step, but it's an equilibrium step. The second step is slow, and the rate law is an intermediate. It's going to be K times ClO2F2. See what I'm saying? So we would replace ClO2F2 with the reactants that made it, which gives us 1 ClO2 and 1 F2 in the rate law. You follow what I'm saying?
Yeah, but don't you need ClO2 to the second power?
No, it was first order. Both the ClO2 and the F2 were first order. Weren't they?
Yeah.
Yeah, they were. Yeah, so you just needed each to the first power.
Well, what about the coefficient? I thought you put that to the power.
That's only for the elementary steps.
Yeah, that's only when it's an elementary step. When you have the overall equation up there at the top, you don't use those coefficients to give the orders. That's why we have this data table, so we can figure out what their orders are. All right. Would you jump now? Let's see. Did we do the mechanism in number 4? We did that one, I think. All right, so jump to number 6. Can I have you try number 6, do just parts A and E. Come up with the order of each reactant, and then determine which of those mechanisms given is correct.
We can do it. Regan, if I finish it before you, then you have to do my
Hurry up, Regan. Will you try to get motivated, please?
It's a second order. Intelligence can't take it everywhere. The first mechanism is wrong, and the second one is correct. I'm not even sure what's that.
Yeah, he's wrong. He's just making stuff up.
No, Sachin, turn it away. Sachin, this is why I'm trying to turn your desk every time. No, Sachin. Sachin, keep working. If he doesn't, I still get $5. You don't. What?
Okay.
They're gonna turn me further.
No, I don't want to do it.
This one is like actually like pretty. I don't know how to do pretty good at it.
Do you A and E?
Yeah, just A and E.
Or actually not like.
E refers you to step B, or part B, but it's just a rate law, so you don't really have to do part B. You know what the orders are.
Yeah, they changed,
Were you able to get the orders of the two reactants?
I need a calculator.
Oh, you can see it without a calculator.
Well, like, one of them is 1.3 times, okay, 10 to the minus 3.
Put your backpack right here. Wait, these are my notes.
Yeah.
This thing, you cannot see this. It's illegal. Don't let him see it.
Danny, it's okay if he does. It's
Can't
okay.
see it.
It's okay.
Danny, I can't hear if you mother.
It's first order. What's first order?
Regan, do you need a paper?
Yeah, I need to pick the
Come here.
Somebody
Okay, it's
spit that
first
shit.
order and it is first
No,
order.
but I have fun.
Today's the last day we'll be looking at these, so I can give these away freely.
Oh, really? I thought we should use that home for Joy.
Oh, you could.
Can this just, for joy, can this just be a homework? No!
Wait, I
Oh,
was right.
no,
We
you
don't
can't.
get- We don't get homework in this class.
I don't know, that's the second one.
Like, he doesn't require you to do it.
Good? So for number 6, do we get first order for each reactant?
Yeah.
First order
Yes.
for each. Now, what about the mechanisms? How do you like mechanism number 1?
It exists.
In mechanism 1, we have the slow step is the second one, and it has an intermediate, of course. What do you notice about that intermediate?
It's,
See how it's not made by an equilibrium? And then it's got that C term in there as well with it, which is a product with it. I find number 1 to be bogus. I don't like number 1. It was not, the intermediate was not made by an equilibrium, and so we're not going to do any substituting for that.
so is there like a reason I would think you don't have
That's what I'm telling you. I don't like it because M was not made by an equilibrium reaction. It has to be, if we're going to substitute it out. How about number 2? Do you like number 2? I love number 2 as well. Yes. Number 2, we do have a slow step including an intermediate. So we replace the M with B, and then we have rate equals K times A times B, which is the rate law. Both of them first order. Agreed? How do you like number 3? Not good. Nope. The slow step is the second one. And when we replace out the M with A and B, we're going to wind up with A to the second order. And then B. Which does not agree with what we found experimentally. You with me? All right. So we've done a bunch of these examples. I think when you do the ones in the book, they're just going to be a piece of cake. Now, there are some that you'll have to find the integrated rate law for, where you have to do the graphing. No, I think you already know that I'm going to give you the graphs. You won't have to do any graphing on the test. We don't have time for that. But I would suggest that you know how to do that. Do at least one of the integrated rate law problems with Excel or with your calculator, with Desmus or whatever, just to make sure that you're comfortable with how those rate laws are achieved, the integrated rate laws. And then these with the time and the concentration and rate. You'll do lots of these. In the book, they're quite easy. Trust me. I have one other thing for you, one more slide. How are we doing for time? Very well. This is the last topic in the chapter. We'll be studying this on Monday, and then we'll have a lab on Tuesday, and the lab on Tuesday is going to use all of this. We're going to find a differential rate law in the lab. It's not going to be a lab write-up. It's just going to be on a handout. So the last thing in the chapter is collision theory. If you want reactions to happen, the particles that are reacting have to run into one another. Now, as you saw in that one example, they don't necessarily, the reactants don't have to run into one another. They may go through a series of steps where they'll creatively react and make products, like they had to in that example. But there's three different considerations that we have to make about the kinetics of a reaction. One thing about collision theory is this, that the colliding particles must have the right orientation when they collide. It's not enough for the particles just to run into each other. They have to be oriented properly. And I'll show you what I mean. Why don't you write that down? I have a picture over here that I'll refer you check this out. Here's hydroxide. Hydroxide is a base. You know what the job of a base is?
To neutralize an acid.
To neutralize acids, right? To take hydrogens, yeah, become neutral. So hydroxides like to take a hydrogen on. This is what? What do you see here? Organic chemistry. What type of compound is this? I see a carbon with a double bond to an O and also a single bond to an OH. Not a ketone, not an ether.
Aldehyde. Aldehyde.
No and no. Keep going.
Oh,
No.
wait, I know it. It's the all thing, the all. It ends in all.
No.
That's an alcohol.
Regan? Carboxylic acid.
Oh my god.
The acid, remember? Acid.
So he definitely knew it. He was just waiting for someone to get it.
Now that I say it's an acid, do you remember acids?
Sure.
C double bond OH?
Oh yeah.
Oh, yeah.
You do. Okay, chemists, what is the name of this acid? It's got 2 carbons in it. Ethanoic acid. Ethanoic acid. Yep. Okay, so anyway, we have 4 hydrogens in this thing. 1, 2, 3, 4. It is an acid. That means it's willing to give up a hydrogen. Which of the 4 acids is it most willing? I said acids. Which of the 4 hydrogens is it most willing to give up? That one. Yep. We're going to study this when we talk about chapter 14, acids. The fact that there's 2 oxygens on there draws the electrons away from that bond, and that makes that a weak bond. So that hydrogen is likely to come off as a free hydrogen. Now, if I have this base, that hydroxide longs for a hydrogen. If it's running against the rear end of the molecule, boom, boom, and just bumping into it, it's not going to react. However, if this hydroxide can be up against, and it runs into the acid molecule, then when it's got the right orientation, this hydroxide will easily snatch that hydrogen right off of the molecule. So that's what I mean by the orientation matters. It matters how these particles run into each other, how their orientation is. So again, yeah, when you have the non-reacting sides of the molecules colliding, they might collide a lot, but they're not going to cause a reaction to happen. So the orientation matters. We'll talk about that more in depth on Monday. The amount of energy that they collide with matters. Reactions can only happen if the reacting things break apart. We've got to break bonds in the reactants, and then they'll rearrange and make new things. So if you have particles that run into each other, and if they don't have enough energy, then there's no breaking apart of the bonds and nothing happens. So they've got to hit each other with enough kinetic energy to be able to break their original bonds. That's where we get this notion of activation energy. That's like the minimum amount of energy they have to collide with in order to react. And the last thing that we consider is the temperature. Temperature is a big deal because if you increase the temperature of a reaction, 2 things happen. Number 1, they'll collide more frequently because the particles are moving faster. So you get more frequent collisions, and since they're moving faster, they're going to hit each other with more force, which means they're going to have higher energy, so there's more likely that collisions will actually cause a change to happen. So yeah, increasing the temperature will always increase the rate of a reaction. This last bullet point is very important. We're going to have a mathematical equation that describes that, but that last bullet is worth highlighting. K increases with 3 things we got to know: temperature, if there's a catalyst present, and the surface area of solids. And that's where I'm going to call it quits for today. We have to talk a little bit more depth about these things. I told you there was an equation coming for the that last thing. take that on next week. Do some problems. Either do the book exercises or the practice test over the weekend. What's on your